problem sorted like one ordered pair. This is 1139 largest one bordered square. Let's get right into it. You're given a 2D grid of zeros and ones. Return the number of elements in the largest square subgrid that has all ones on its border, or zero if such a subgrid does not exist in the grid. Okay, what does that mean? Well, essentially, you're given a grid like this example. Your grid is what exactly? What are we looking at here? We're looking at this grid, and I'm going to make myself smaller. Now, I am a handsome man, but I'm not handsome enough to justify taking up that much real estate. Okay, so we have the grid, which is, if we reorder it, 1, 1, 1, 1, 0, 1, 1, 1, 1. And then you'll notice that there's a square in this position, and that square has 9 elements. How do you know it has 9 elements in total? Well, you know, it's a square. You take the area of the square, that'll give you the number of elements, right? So it's a 3 by 3, so 3 times 3 is 9. Or you could say there's 1, 2, 3, 4, 5, 6, 7, 8, 9. But of course, you know, the length of the side squared, that'll give you the area of the square. So this idea of border is that only the edges, right? Only the border of the square has to be ones. Whatever's inside doesn't matter, right? So more generally, we could have a system where it doesn't matter what's inside, right? We could have x, 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 right? But as long as the external side, when I'm putting x's here, I'm saying it's variable, right? It could be 1 or 0. As long as this external side is all ones, then we have a valid solution. And in this solution, quickly computing it, what would be the number of elements? We would have 5 by 5, 25, right? So we would return 25 if this was one of our examples. Okay, so this problem is very similar to kind of like a subclass of dynamic programming problems that is pretty common with these grid. It's a grid style dynamic programming problem, and it's very closely related to this idea of finding the largest square in a matrix where it's all ones. The kind of difference between this problem and that problem, and if you haven't solved that problem before, I'd recommend that you solve the largest square of ones in a grid. That whatever that problem's called, you look that up, you'll probably find it before you solve this one, because this one's kind of a little bit more difficult than that one. It's kind of built on top of that one, the ideas in that one. So it might be beneficial to solve that first, but I'll do this problem independently. But just understand that I have intuition that I've gained from solving that problem. So I may not be completely all-encompassing in terms of how I describe this problem, because there is previous problems that I've solved. So it can be difficult. You do the same thing so many times, it can actually become difficult to explain how you're doing it, right? You can just do it. But that's more of a philosophical point. But that doesn't matter. So when you're looking at this, right, I guess the dynamic programming idea is like, well, if you have saved information about what it takes to make a square. So to make this square, we don't care what's on the inside. We only care about this perimeter, right? The border of the square that we can use to create the square itself. So basically, if we had information about the arms, we could use that information to determine kind of what kind of square we can build. So what I'm saying by that is, like, at any position, right? If we thought about a position here, and there seems to be a significant delay, and I don't know why. And if we thought about, okay, if there's ones this far in this arrow's direction, right? And that's 4. And there's ones this far in this arrow direction. The only way this whole thing could be a square is if there's equal and opposite ones in the opposite corner. Okay? So if I have a leg that's like length 4 this way, and another leg that's length 4 up, right? So if I have a leg that's length 4 to the left and length 4 up, in order to create the whole square, I need to have a leg that's length 4 down and length 4 to the right in a diagonal position, right? So if I have length L to the left, meaning that there's a leg to my left that's length 4 in this position, and we'll call this position IJ. Right, so in position IJ, I have a length 4 to the left and length 4 up. So if I have length 4 to the left, length L to the left, and length L above, position IJ, and we'll color that green just so that there's some sort of consistency in the madness, which is me just explaining things. Right, so if I have length L to the left, so L's 4. So for any position, if I have an arm to my left, that's length 4, and I have an arm above me, that's length 4, then I have a square. Then I have a square of length of area L squared if what? If I have also length L below, or let's do it the right way. So length L to the right in position what? So if I have length L to the left and length L above, I kind of want to connect this square, right? Because I only have information about these two sides. So if I want to know, well, how do I know if there's what completes this square? Well, I'm going to need length L to the right of this position. And this position is I minus L, J minus L, right? So this position here is I minus L, J minus L. Right, so I need length L to the right in position I minus L, J minus L, and below. And L below in the same position. So basically what that means is if we keep information about all the length of all the limbs in all directions. So I keep the length of the limbs. When I'm saying limbs, if I didn't articulate that well enough, I'm basically saying the length of the longest like line in any direction, right? So if I have information at any point about like I'm in the sea of nothingness, right? So let's just draw out a grid really quickly. All right, so I have this grid. And it just turns out that there's a length 4 to the left, like this, right? So I check this position, and this position says there's something 4 to the left, and there's something 4 above. In order for this square to be completed, there'd have to be something here that tells me that there's something 4 to the right and 4 below. So in order to do that, we'll just use like a prefix sum idea to keep track of the length of the limbs, the length of the lines. I keep saying limbs and legs. The length of the line in each direction, and then use that information. So basically in this example, right, let's do the actual example here. So we have this grid, right, which is 1 1 1 0 1 1 1 1 1. And then we'll create 4 arrays. One that tells us the length of the limbs to the left, one that tells us the length of the limbs, the length of the lines below us, one that tells us the length of the lines to the left of us, and one that tells us the length of the lines to the right of us. So we'll have this left one. We'll call it left, I guess. Very original. Right, and this will tell us the length of the limbs to the left. So this has length 1, 2, and 3. So what does that mean? Well, because you notice here there's a length 1 limb to the left. So this is 1, right? There's a length 2 limb to the left at this position. So this is 2. And there's a length 3 limb to the left. So this is 3. Okay. This is 1. This is where it gets interesting, 0, right? Because there's no limb, there's no line to the left here because this is 0. And this is 1. And this is 1, 2, and 3. And we'll do the same thing for... We'll call it above. Sometimes I wonder if it's even worth it to show my face, but, you know, at least you know there's a real person here and I'm not, like, in my pajamas. Well, sometimes I am when I solve these problems, but I don't know what the benefit is. There's something about people seeing someone and knowing there's someone real there on the other side. So this is 1, 2, 3. Why is it 1, 2, 3, right? Because there's a length 1 line going up here, length 2 line going up here, length 3 line going up here. 1, 2, 3. 1, 0, 1, 1, 2, 3. And then let's just try to quickly do this. I think I might have done this a stupid way. Maybe I'll reorder them if it makes sense. Yeah, I will. I know what I'm going to do. I have an excellent idea. So let's quickly, and if you want to speed through this, if I'm just, annoying you by how long this is taking. But it's good to just walk through this so you can see how this works. Okay, so to the right, there's 1, 2, 3. 1, 0, 1, because there's a there's a line of length 3 at this position, right? There's 0 here. There's only 1 here because it's just this 0 discontinues that. 1, 2, 3. And then below, there's 1, 2, 3, 1, 0, 1, 1, 2, 3. All right. And then we're going to reorder this so it's kind of makes sense in terms of what things are relative to other things. So we have this system here, right? So when we look at any cell, we could say, okay, what's to the left of this cell? 1. Okay, so there's only 1 to the left. There's 1 above. So let's color these actually. So let's make the left one. Sorry, I'm trying to think about some colors so this can all be kind of cool, I guess. Yellow, red, and white. That's fine. Okay, so when we look at this first position, 1 left, above 1, 3, 1, 3 down. That's basically saying, okay, we know then at this position, just by using these cached information, I have something to the left that's 1, and something that above that's 1. So the maximum square I can make here is size 1. So that's not really going to give me anything interesting. And you do the same thing over and over again. Let's just skip forward until what? So since the square is so small, let's look at this position here. Okay, to the left is 1. Okay, let's do this one. So this position here, we have to the left 2. Okay, so we have to the left 2. I'm using this information here, right? We have above 1. So since we only have above 1 like this, we know the maximum size square can only be size 1. So it's the length, the minimum length of both your limbs, your left limb and your above limb. Okay, so that doesn't really give us anything. What about here? So here your left is 3, right? Your above is 3. So in order for the square to be fit here, what positions can we check? We can check this position to see if we make a square of length 2, or this position if we make a square of length 2. How would we do that? So first we would check here, it'd be 0 below and 0 to the right, so we can't create a square. We could check this position here. And at this position, we get below 3. So just by looking at this information, we get 3. And then looking at this information, we get 3. So now we know we have a square. So notice how all I have to do is populate left, populate above, populate right, populate below. And then for any position, I can say, okay, what's the length of my left at this position? What's the length of above at this position? And in the corresponding corners, right? So that will give me the dimensions in one corner, right? That'll give me information about the dimensions in one corner. And then I check each of the other potential corners, right? So I check this corner, see if it works. Check this corner, see if it works. Check this corner, see if it works in making a square. So that's what we kind of did here. So we checked this corner. We found out the maximum size that we could get. And then we checked these positions to see if we could get the other corner. So we're basically traversing to see if we can get one corner of the square, which is like 2 sides, the left side and the above side of the square. And then we try to find, the other corner of the square to see if we can fit it. Okay, so that's the basic idea. So with that, let's just try to solve this because I've spent way too long trying to make this work. But that's the basic idea. So let's populate left, above, below, and whatever. So we have left, above. We have left, right, above, below. And then those will just be equal to the grid as they are. So G copy the grid for G and grid. And we're going to have to do this 4 times. Put this on 2 lines. so people don't go crazy on me. Okay. G for grid, G for grid, G. Okay. And then what we'll do is we'll say, okay, we'll look at each row. And then each column. And we'll say, okay, if grid at ij, or no, we could say if L, because you only add 1 to the length, right, if there's already an element in there. If there's no element, right, like here, there's no 1 in this position, so it's 0. You don't add in the previous thing to the left, right? Here you add in the previous thing to the left because there's a 1, and the previous one was 1, so it becomes 2. Since this is a 1, you add in the previous thing, which is 2, to make it 3. Even though this is a 1, since this is 0, you don't add the previous thing. So if left I of j, then left of I of j plus equal whatever comes before it, I j minus 1. Okay, and then we'll do the same thing for range length of grid. So now we'll do the right as well, length of grid minus 2, negative 1, negative 1. Okay, this is just a lot of repeating stuff. There's probably a better way of doing this, but I don't know. But then now would be to the right. Okay. And then we want to go above and below. And when we write our code, we go above and beyond. So this would start at length of grid. Oh, this is a square grid. I mean, this is not necessarily square, so don't let yourself make that mistake. Okay. Right, again, it's not necessarily square. For I in range, length of grid, we'll go from 1 to the end. And then we'll play the same game for I in range from the end, excluding the last one, to 0, go in the negative direction. Okay. And then this is pretty similar, so I'll just copy that. Okay, if we're going above, goes above, if I minus 1 above j, and then we're doing below. So I'm just doing the prefix sum for this. If this doesn't make sense, you know, this is just a prefix sum idea. I'm trying to find the length of each of the limbs. I'm essentially just populating these left, right, below arrays from the original array. This is I plus 1. Okay. And then just so you can see if this works, right? So we want to do above. So we'll print for A and A. We'll print A. So does this look like A? Does it look okay? I'm not sure what I'm doing today. My life's not so great. It's actually kind of lame. I don't know what else to say. Okay, so should be 111 202 313. Okay, what about left? So let's print left, and that should give us 123 101 123. 123 101 123. Okay, right. And it's never a bad idea if you have time in the interview. Maybe don't do it how I'm doing it right now, like one at a time. Just try to print all of them at once, but you know. Right is 321 101 321, and then below. I don't even need to change that. It's fine. And then below, it's 321 101 321 321 101. Okay, so then this works. So then now we just need to find what the largest is, right? So we'll do the largest bordered square is 0. We'll call it LS for largest square, I guess. It's fine. And at the end, we'll return that largest square. Okay, so we'll basically do this, right? Because we'll look at each cell and see if we can find a square at that cell. Okay. Now, the length of you're trying to find, you know, at any position, you're going to have the length of the left limb and the length of the limb above. So the largest square you can make, what are the possible squares you can make from this position? Well, you can't make this square, right? Because it overshoots this limb. You already know the minimum square you can make, or the maximum square you can make rather, right? The maximum square you can make is this one. But you could also make a square fitting these, and you could also make a square fitting these. So you need to check all possible corners, right? You need to check this corner and this corner and this corner for this edge, because there could be a corresponding square with those two limbs in those positions. That's the basic idea of this problem, right? So I could say, well, I'll look at each square in those positions. So I'll look at K. I'll look at K in range. I could be just a square myself. So the minimum of what's to the left at this position and what's above this position, right? Because that's the maximum size square I can make, right? The minimum of this and this correspond to the maximum squares that I can create. And then I'll check each of those possible corners, right? So if the minimum of what's to the right of I minus K, J minus K, right? Because that's the position here, right? Like if K is 1, there's a length 2, right? So this is 4. So if we walk through this example, right, this would be 4, and this would be 1, 2, 3, 4, 6. Right, the minimum is 4, so I would do K equals 0, 1, 2, and 3. Right, so let's say when K equals 1, if this is position ij, we'd want to check this position, which is I minus 1, I minus k, j minus k. I minus k, j minus k, I minus k, j minus k. Those positions. And we want to check if the length of what's to the right would be 1, 2, 3, 4. So if k is 3, then the length of what's to the right needs to be 1 more than that, right? So the minimum of what's to the right and what's below, right, because that would be the other edge of the square, since I've already established what square can exist to the left and above. Now I need to attach what can exist if I look at what's below and what's to the right. So what's to the right and what's below with the same I minus k, j minus k. If the minimum of that is greater than or equal to k, right, because it's possible that this thing, right, what's below here could be like crazy long, right? It could be like at this green position, it could be like this, right? But I know at least, right, as long as it's at least larger than this position, as long as it the line going down here overshoots where k is, then it's going to make a square. So if it's larger than or equal to k, well, then that means that we have a solution. So we could say ls is the max of ls. And what square do we have here? Well, you'll notice here, right, when k equals 3, it corresponds to a size 4 square. Right, so we have k plus 1, because if k is 3, that means we have a size 4 square. If k is 5, we have a size 6 square, so it's k plus 1 squared. So then we just check that for each possible square. All right. We submit that and we cry because it doesn't work. Okay, so what is the time and space of this? So for time, let's do space first. So for space, we have to create 4 copies of the grid essentially, right? And then we just populate those 4 copies. So that's 4n squared if it's, or 4n times m. One second, I got someone at the door. Hello? I'm making a video. All right, so if we had n equals the length of the grid and m equals the length of grid 0. For space, we're going to have to create 4 copies of the array. So that's 4n times m, but we'll just call that n times m. Okay. Now for time, well, we have to look through the whole array and then do it twice. So that's n times m time. This is n times m time. We're going to have to do it again, so we're going to have to look at all n times m grid cells. But for each n times m grid cells, we have to look at the left and the right. Right? We have to look at essentially each possible corner, right? Because when we have like arm this direction. We have an arm to the left and an arm above. We have to look at this position and this position and this position. And you can kind of see it here, right? So it's possible that that spans the whole size of the array. So it's definitely O(n) times n. And then we'll just say that one of these is larger than the other, like n is larger than m or m is larger than n. So whatever the max of that is, we'll call that n, right? So we'll say that n equals the max of n and n, n and m, right? So it's n cubed. So for time, oh, that was space, I messed it up. So this is big O of n cubed, and this is just n squared space. So n cubed time n squared space. All right, guys, kind of a weird problem, but a fun one. Peace.